Hey there students, Mr. Puget here. In our video today, we're going to be looking at a sample problem involving the concepts of work and energy. Depending on the year in which you're watching this video, this will show up either on homework 7 or 7A. But broadly, here we're going to be looking at an object that experiences a few forces and what's going on with the energy of that object. So let's talk about the setup of our problem. So here we have a block and we're told that the block is getting pulled at an angle across a flat surface. So to give us a little visual here, we've got a block, and we are told the block is being pulled at a certain angle. I'll call this F, let's say applied, or we could say F pull. We're told a few other things about this system before we jump in. We are given the mass of the block, just to take into account of things. My number here is 17.7 kilograms. So we're given the block's mass. We're also told the magnitude of the pulling force. My value is 197 newtons. So we're pulling with a pretty sizable amount of force here. And we're told the angle of our pulling force with the horizontal is 29.2 degrees. So 29.2 degrees, okay? We're told the block is displaced 27.5 meters. So again, picture not really drawn to scale here. The block travels a displacement 27.5 meters. I'm just taking into account all of our numbers here. And we're told that there is some friction here on the surface, so I'm making sure I read this correctly. And we're given the coefficient of kinetic friction. Use of K is 0.148. So mu K, 0.148. So a lot of things to keep track of. This is something we oftentimes want to be careful of when we start a problem, is making sure we understand what each piece of information is that we're given, kind of how that fits. We have the block's mass. We're told that the block is getting pulled at an angle over a certain distance. Maybe that's an indication that there's some work being done here. But there's also a force of friction, which is probably going to come into play here a bit later. So there are a couple of parts of this problem. We're going to work through a couple of them together. So the first question that we're looking at is, what is the work done by the pulling force? Okay, so kind of part one of this. So we want to find the work done by the pulling force. How much work are we doing as we pull the block across the ground? Now, we've been looking at, as we've been studying these ideas of work and energy, two main equations for work. One is our work energy theorem, where we can find how much the total energy of a system changes. That will equal our work. We've also been looking at our work equation, that the work done is a product of the force applied on the object, its displacement, that sort of thing. Given how the problem is laid out, we know how much force we're applying on the object from the pull. We know how far we're displacing the object. So I think the work equation is going to be our better approach. So the work done by our pulling force is equal to the magnitude of the pulling force multiplied by the magnitude of our displacement multiplied by cosine of the angle between the force and the displacement. We're on my way. Okay, so let's see what we have here. Coming back to what I wrote down a moment ago. Okay, we know the magnitude of our pulling force, 197 newtons. And the magnitude of 197, just 197. We're told our block displaces 27.5 meters. The magnitude of 27.5 is 27.5. And we need the angle between our force and displacement. So we have to be careful here. Just because we're given an angle doesn't always mean that's the angle that will go into our work equation. Here's what we do. Take one hand, point that in the direction of the pulling force, or whichever force we're looking at. Here, pull force. So up and to the right. Which way is our displacement? Horizontally to the right. So is the angle given the angle between those vectors? Meaning, is it the angle that touches both vectors? And you can see here, this represents our delta x. I don't necessarily want to put an arrow there necessarily, but you can see that our angle is the angle that touches between our force and our displacement. So we can use 29.2 degrees here as our angle. So cosine 29.2 degrees. Okay, so now we should be able to input each of our values and find our work done. Now where's my calculator here? So 197 multiplied by 27.5 multiplied by cosine of 29.2. Sure, I'm in degree mode, which I am. Okay, looks like I'm getting 4,729 joules. Let me double check that. Looks good. So 4,729 joules. if the question was asking, we might convert this to kilojoules. So I can divide by 1,000 because there are 1,000 joules per 1 kilojoule and something like 4.73 kilojoules. I believe the question here is wanting our answer in joules, so we'd go with this value here. So here's the work done just by our pulling force. Now that may not be the overall amount of work done because there are some other forces that will be acting on the object. Remember, we were told that there was some friction here we'll probably have to account for. I'm guessing that's where the problem wants to go next. But here we can find the work done by one of the forces on the object, namely the pulling force. Okay, so hopefully that gets us going here with part one. I'm going to look at part two, and it says this. Find the magnitude of the work done by the force of friction. Okay, so again, part two. Scroll down here a little bit. Part two is this. We want to find what is the work done by our force of friction. Now, we might be able to stick with the same approach. We could use our work equation. That's going to require us to do a little bit more work. No pun intended. Kind of pun intended. We don't really have enough information to look at the energy here because we don't know anything about the speed of the object. Now, it is on flat ground, so we can assume there's no gravitational potential energy, and there aren't any springs mentioned, but we just don't know anything about the speeds right now. So it's kind of hard for us to go with the work energy theorem. So let's jot down our work equation. Work done by our force of friction is equal to the magnitude of that force multiplied by the magnitude of our displacement multiplied by cosine of the angle between our force and our displacement. Now, if we look back at the problem statement, well, we know the displacement of our block. We pull on the block for 27.5 meters, and it's reasonable for us to assume the friction is acting that entire time, right? So the entire time we pull the block, friction is an active force on the object. So our delta x here would still be 27.5. The problem is we don't really know the force of friction. That's where we may have to go. We do know, however, the coefficient of friction. I'll write that down here so I don't have to keep scrolling back up. Come on now. I'm going to write down u sub k is equal to 0.148. Now, a few things we want to be careful of here. It's very tempting to use that coefficient and plug that in for your force. Remember, the coefficient of friction is not the same thing as the force of friction. This is a value that represents how rough the surfaces are that are interacting, the block and the ground. Our force of friction we can find by taking our coefficient of friction and multiplying by the normal force. Again, the force of friction is a force, it should have units of newtons. Our coefficient of friction, it is a unitless value, usually around 0 to 1. So, in order for us to find our force of friction, we need to find our normal force. So this is going to require us to do a little bit of work with the forces on the object. So, what we're going to do here is we're going to take a side step so that we can try and find our normal force. Once we have that, we should be able to find our force of friction and bring that over here. Because we want, what's our force of friction? We know our displacement is 27.5 meters. And we'll talk about the angle here in just a moment once we get through dealing with the force. So, here's what let's do. For us to analyze forces on an object, we need to draw a free body diagram. So, what forces do we have here? Well, we can assume pretty safely here that we're on or near Earth's surface. So there will be a gravitational force from the Earth onto the block. Okay, the block is touching the, just as the surface here, so the ground. So there will be a normal force here, Fn. That's the force we want to solve for. So hopefully we can get there. We also have our force of friction. Ooh, that is not the direction of our force of friction. This is our pulling force. And then friction, remember, is a force that resists sliding. So if the block is sliding to the right, based on the picture, friction is going to act horizontally to the left, F sub k. Okay, so now we're back. So we have our forces acting on our block here. Now we need to see if we can figure out what's going on with our force of friction. Again, to find that, we need our normal force. So let's look at what's happening with the forces in the y direction. So, if you remember, normal force is one of those forces that we don't have an equation for. Some of the forces that we've been learning about, we have equations for, some we don't. But in order to find our normal force, we can use Newton's second law by summing up all the forces in a given direction. So, Newton's second law states that the sum of forces on an object should equal the object's mass multiplied by the object's acceleration. Here, since we want to find what's going on with the normal force, we're going to look in the y direction. Now, what forces do we have in the y direction? Well, we have our normal force and our force of gravity. So I've got my normal force, Fn. I'm going to call that positive because it's pointed upward, which is our standard direction for the positive y, minus my force of gravity. Again, I know Newton's second law does say sum of forces, but remember, when we are adding forces, forces are vectors. So I need to account for the direction of that force. That's why I'm subtracting the force of gravity. Now, our pulling force. Technically, our pulling force is kind of in the y direction, partially, because it's at an angle up and to the right. That means a part of that force is directed in the x direction, positive x. A part of the force is directed in the positive y. So when I'm summing up the forces here, I need to account for just the y component. Remember, a component is a part of a vector. So here, I need to add the y component of our pulling force. I'll call that Fp, comma, y, the y component of the pulling force. Now that should equal our object's mass, 17.7 kilograms, multiplied by the object's acceleration in the y direction. Now, when I look back at the problem, it says the block is pulled across the ground. Does not mention anything about a change in our speed up or down. So we're not speeding up, we're not slowing down vertically. We may be accelerating horizontally depending on everything that's going on with the forces here. But we should not be accelerating vertically because we're moving across a flat level surface. So 0 meters per second squared. And again, any number multiplied by 0 is going to give us 0. Okay, so let's see what we can find here. We have a way to find our force of gravity. Let's start with that. Because if we can find our other two forces, force of gravity and our y component of the pulling force, we should be good to go to find our normal force. So F sub g, force of gravity, we can find that by using the object's mass and local acceleration due to gravity. We're assuming we're here on Earth, so that's the value that we'll use, 9.81 meters per second squared. And mass of the object was 17.7 kilograms. So 17.7, 9.81 meters per second squared. Let's multiply those together. 17.7, 9.81, 173.6. Okay? So that takes care of one of the forces that we need. We also need the y component of our pulling force. How are we going to get there? Well, if we look back at our original drawing, we have the overall magnitude of our pulling force. So the pulling force is 197 newtons at an angle of 29.2 degrees. So, over in there a little bit. That means this value, 197 newtons. This is our angle theta. We want to find the y component, so opposite to hypotenuse. If I remember my trig functions there, SOHCAHTOA, so sine is equal to the ratio of our opposite side divided by our hypotenuse. We want the opposite side. I have the hypotenuse, so I would write down this. Sine of our angle, 29.2 degrees, is equal to the opposite side of our force triangle here, or really our force vector, which is the y component of our pulling force, divided by the hypotenuse, 197 newtons, I should say. Then I can multiply by 197 up to the numerator. So 197 multiplied by sine, 29.2, I get 96.1 newtons. Okay. So now I can plug those values in. I have Fn minus my force of gravity, 173.6 newtons, plus 96.1 newtons is equal to 0. I can then combine these terms, negative 173.6 plus 96.1, so I get Fn minus 77.5 newtons is equal to 0. I can add 77.5 over, and now I can show that my normal force should be equal to 77.5 newtons. So a little bit of extra work to get there. Oftentimes, in many of the situations that we've looked at, our normal force and our force of gravity are equal, but since we have that extra pulling force here, that's going to affect what our normal force is. Remember, our normal force is a measurement of contact between those two objects, and if that pulling force is there, that can actually affect what happens with the contact force. That's why we don't have one set equation for normal force, because, well, normal force, that contact, is really a result of some of the other forces and interactions there. Well, I should say, it can be influenced by some other forces. Okay, so all of that work was to get us to our normal force. Why did we find that? So that we could come back and find our force of friction. So now I can plug in my coefficient of friction, 0.148, and the normal force, 77.5 newtons, and I will get 11.47 newtons. I know that's 4 sig figs, but I'll go with that now. Don't want to do too much rounding as I go throughout so it doesn't affect my final answer too much. So now our force of friction, magnitude of 11.47 newtons, over a displacement of 27.5 meters, and then cosine of the angle between our force and displacement. Well, we said from our picture that the box is getting pulled, well, it's getting pulled up into the left, or right, I should say, but it will be moving across the surface, so to the right. Our force of friction is to the left, so between those, we have an angle of 180 degrees. So, I'll plug in cosine of 180 here, which if I remember that should be -1, so the work we get here should be negative 11.47 multiplied by 27.5 times cosine of 180. So I get negative 315.4 joules. Now, is that what the question wants? It does say find the magnitude of the work done, which means I'm going to basically take an absolute value here. The magnitude of the work done is 315.4 joules. Now, again, we have to be careful here. The work done is actually negative based on how we've defined our direction, which means friction is actually stealing energy. All the question wants here is how much energy does it steal, is what it's saying. It does not necessarily want us to say what's the total work done in terms of positive or negative, just how much work is being done overall. So, if you do try a negative answer in there and you're getting it wrong, remember the question wants the magnitude. Remember, we just want to put in basically an absolute value function at the end and treat that as a positive. So, a bit of work here to get to what we're looking for, but hopefully this gets us moving here in the right direction. This is a great problem that deals with a lot of our concepts, with things like energy and changes in energy, aka work, as well as integrating some concepts on forces. So hopefully this gets you moving in the right direction on this question. As always, if you have further questions, feel free to reach out and let us know. Other than that, good luck.